pieces of software. The first is what is called AFTP, which is just adiabatic flame temperature program, okay? And then the second one is the one that you've already used. You used the Cycles simulation program for lab number 2. Well, you're also going to use that for lab number 3, but you're going to use it differently, right? Rather than use the ideal thermodynamic cycle analysis, you're going to use the fuel air analysis option that you have available to you, okay? So you have to make sure that you make that correct selection when collecting your data for objective number 2, okay? Now, something that's really important to note is that for all of the studies in both AFTP and Cycles, AFTP, by the way, is in the same file location as the Cycles software is located. But for all the studies that you do, objective number 1 and objective number 2, you need to make sure that you select this use full equilibrium calculation option, and I'll show you how you activate that for the 2 different programs below. But it's really important to do this because this will allow you to generate data that looks like what we've talked about in class, okay? If you don't select this option, a lot of your results are going to be erroneous, and you'll actually describe wrong data. And so it'll be difficult for us to grade your assignment correctly because your analysis will all be geared toward the wrong set of data, okay? So we need to make sure that you remember to do that as you run through these 2 objectives, okay? So as was already described, objective number 1 is having you do a study of the adiabatic flame temperature and emissions. And so you'll use this AFTP simulation program. You'll find it under the same folder where you found Cycles from your lab number 2. And then this is really important, these 2 steps. This is how you essentially select that full equilibrium calculation. For step number 1, you have to go to the File menu, and then you have to select the option Load Thermodynamic Data, and under that, select the file thermodata1.2.22.cyd, okay? And you will click Open, and what that does is it loads all of the necessary thermodynamic data into the program so that you can do these full equilibrium calculations that you'll select in step number 2, okay? So it's possible that the file is going to be located in the installation folder. So if you install this on your own computer, you kind of have to hunt and peck for it a little bit. You could just type into a search menu that file name. That might be the easiest way to find it. On my computer, it was located under this file path here, okay? But it might be in a different location on your computer. You shouldn't have any issues with it on the VOL, but if you do, please just let me know. So then once you get that file data loaded, you then go to the Options menu, and then that's where you select Use Full Equilibrium Calculation option, okay? And again, that'll activate this proper calculation. If you remember when we talked about equilibrium in class, and we had that big combustion reaction that had 11 unknowns, that full equilibrium calculation is basically solving that combustion reaction, okay? It's really cool stuff. Okay, now in terms of doing the study itself, so this is, what we've talked about so far is just the semantics of getting the program going. Once you're ready to actually commence the study, you're going to do basically 3 different studies, okay? Or excuse me, 2 different studies. The first study is going to be to study flame temperature and emissions with equivalence ratio. And then the second is going to be to study flame temperature and emissions with EGR level, okay? So for studying flame temperature and emissions with equivalence ratio, right, essentially what we want you to do is we want you to explain the behaviors of constant volume, adiabatic flame temperature, and emissions as functions of equivalence ratio, okay? So I then give you some instructions to follow for how to execute the AFTP program properly so that you generate the right data. I give you some tips on how to extract that data from the plots. And then, you essentially will pull the data, you'll make your own plots, and then I give you some instructions on which plots to make, okay? And what I advise you to do is to create two plots. One is adiabatic flame temperature versus equivalence ratio. And then the second are the major and sort of minor emission species, CO2, O2, CO, and H2 versus equivalence ratio, okay? So you'll create those two plots from the data that you collect, and then you'll generate a lab report. And in that lab report, you want to include those plots and the other plots that we'll talk about for the rest of Objective 1 and Objective 2. And then what I need you to do is to, in detail, describe and explain the behaviors of each of the plotted parameters. That is adiabatic flame temperature, CO2, O2, CO, and H2 as functions of equivalence ratio, okay? You're going to do EGR level in the next portion of this study, but for this one, you're describing these behaviors as equivalence ratio changes, okay? Now, I want to make sure that you focus on these 5 elements when doing your write-up, okay? You first, and we haven't gone over this in class yet, but we're going to go over all of these plots in class so that you have the information to be able to do these write-ups, okay? So first, I want you to describe the general behavior of flame temperature as equivalence ratio changes. Then I want you to identify the equivalence ratio where peak adiabatic flame temperature occurs, okay? I'll give you a hint, it's not at 1. It's not right at stoichiometric. We'll talk about this in class. And then on C, I want you to describe the slope of flame temperature for lean equivalence ratios relative to the slope of flame temperature for rich equivalence ratios. And then to describe the general behavior of CO2 and O2 with the equivalence ratio, and likewise the general behavior of CO and H2 with the equivalence ratio. We actually started to do that D and E in today's lecture, right? When we were looking at that plot of data of emissions, right? There was experimental and simulation data, emissions as a function of equivalence ratio, and I was explaining the difference of, how you use data points to describe experimental data, and you use lines to describe calculated parameters, right? So we've already started to describe and explain some of this already. Okay, now the second portion of objective number 1 is to study flame temperature and emissions as a function of EGR level, okay? And so it's going to be very similar to the first portion of the study. The difference, though, is that what I want you to do is you'll vary EGR case, you'll vary EGR levels, okay? So 10%, 20%, 30%, and 40% EGR levels. And I give you instructions on how to do that. And then I want you to create 2 plots, one adiabatic flame temperature versus equivalence ratio with all the EGR cases plotted. And then secondly, nitric oxide versus equivalence ratio with all the EGR cases plotted, okay? And so in your lab report, again, what you'll want to do is use those 2 plots and describe these 5 things, okay? So describe the general behavior of flame temperature with EGR level, describe the changing equivalence ratio of peak adiabatic flame temperature as EGR level increases, describe the general behavior of nitric oxide with equivalence ratio, describe the general behavior of nitric oxide with EGR level, and then describe the changing equivalence ratio of peak NO as EGR level increases, okay? And again, we'll be talking about all of this in class. You don't have all the information to be able to write up your lab report right now, but we'll be discussing all these and basically providing the content that you'll need to know for your lab number 3 write-up in class over the next few weeks. Okay, now that was objective number 1. The lab has objective number 2, and this now is where we actually get to do the internal combustion engine cycle analysis. And so we'll be doing a study of cycle efficiencies of a cycle using a reactive mixture, which is basically an internal combustion engine. Okay, so I give you important instructions here on how to actually run. So for this objective, you're going to go back to using the cycles program, the same program that we used for lab number 2, but using it differently, okay? And I give you some instructions on what you need to do to be able to do that program execution, okay? And then I also ask you to create 3 plots: fuel conversion efficiency as a function of equivalence ratio, thermal efficiency as a function of equivalence ratio, and then combustion efficiency as a function of equivalence ratio. Okay? So again, you're going to include those 3 plots in your lab write-up, and you want to then describe in detail these, actually part A, really. Part B is more discussion. So for part A, you want to describe the general behavior of each of these efficiencies as equivalence ratio varies, okay? And again, we're going to go over that general behavior in class, in lecture, so you'll be able to use all of that content to basically write up your lab report, okay? Now, part B, what I ask you to do there is to basically identify the differences between the results that you obtained from the ideal analysis assumption, that data which you used for lab number 2, and that which you acquired for this lab assignment, fuel air combustion analysis assumption, okay, this lab's results. And so again, this is just a discussion point. You don't need to plot any data for it, and you definitely don't need to rerun the simulation using ideal cycle analysis, okay? It's just a discussion to kind of synthesize what those differences are. And we've actually mostly talked about those differences already, but you'll have a chance to, we'll have a chance to describe them in some more detail as time goes on. Okay, so that's the end of this little ditty about lab number 3. I encourage you, as always, to get started on it as soon as you can and fill in the gaps of information as we learn about it and discuss it in lecture. Thank you very much. If you have any questions about it, by all means, send me an email or visit me during my virtual office hours. Otherwise, wishing you a great day. Thank you. Bye-bye.